Good morning, everyone. This first lecture, I just want to talk about the basic particles of which everything in the universe is apparently made. The atoms, the protons, neutrons, and electrons that make up atoms, and the forces through which they interact with each other to cling together and to do the things that they do, to chemical reactions that occur inside our bodies and everything, nuclear processes that occur in nature. These basic particles and forces are important to understanding how atoms work and how they interact with each other to make all the dynamic things of this universe. You know, we live in a kind of an amazingly complex universe. There's millions of different species of living things on the Earth. There's thousands of different minerals of which the rocks are made up. There's just all this variety in nature, and it's kind of surprising that it boils down to that everything is made of a relatively limited number of types of atoms, but that is apparently the case. And here's a crude diagram of an atom. The dot at the center is supposed to be the atomic nucleus, and then the blue area is the part occupied by the electrons. The electrons sort of cluster around the nucleus. And I've got a note on there. The nucleus is about 100,000 times smaller than the whole atom. So this dot is actually drawn about 1,000 times too big in diameter to accurately represent the relative size. It's kind of hard to believe that an atomic nucleus is that much smaller than the whole atom, given that atoms are so small to begin with, and given that most of the weight of an atom is in its nucleus. Protons and neutrons have about the same mass as each other. They weigh about the same, but they're both about 1,800 times heavier than an electron. So you are, by weight, you're mostly nucleus, right? But almost none of your volume is nucleus. All the mass is concentrated in those really tiny atomic nuclei at the centers of atoms. That fact that nucleons, protons and neutrons, are so much smaller than electrons, that's usually not, people don't usually hear that in a science course, but I think it's kind of important to understanding things like the difference between a nuclear process and a chemical process. And so I'll be going over this idea that the nuclei are so much smaller. So here's more crude depictions of protons, neutrons, and electrons. Once again, the protons and neutrons are actually drawn way too big to accurately represent their size with respect to an electron. And these particles don't have to be round. As we'll see later, they can take different shapes depending on where they are and what they're doing. But the proton and neutron are similar to each other, and they make up the nucleus of an atom, and then they're surrounded by the much larger, lighter electrons. The first person to have a really more or less accurate theory of the atomic theory of matter, the fact that things are made up of these smaller atoms that have different types, was John Dalton, and this was about 200 years ago. Now, philosophers before that believed maybe things are made of tiny bits, but they didn't really have any scientific evidence for it. John Dalton did have evidence in the early part of the 19th century, the early 1800s. And in fact, here is part of a publication of his, and you can see at the top of this left page, these are supposed to be the elements, the basic bits of which matter is made. And he's got some named here: hydrogen, azote, which is what we now call nitrogen, carbon, oxygen, phosphorus. So they knew that there were these elemental particles of which the larger particles are made. So here he's got what we would now call a molecule of water. He thought it was one oxygen and one hydrogen. We now know it's one oxygen and two hydrogen atoms. And he's got a bunch of these composited particles, what he thought at the time they were made up of. So they knew about elements. They knew that these different molecules, these different what we call compounds, are made up of these smaller bits, and there's a finite number of different types of smaller bits. They didn't have all the elements back there, and you can see this list up here: zinc, copper, lead, silver. Those all are truly elements. Now there's a couple in here that are not elements, like soda is not an element, that's a compound. They thought at the time that it was an element. Turns out that's not the case. But they had some pretty good information at the time. Over the last 200 years, this has evolved. And this is the modern periodic table of elements. So this is all the different types of elements we have. Now this list goes all the way up to 118. We don't have that many elements on Earth. There's about 90 of them that exist on Earth. This entire bottom row on here, none of those elements is stable. They're all radioisotopes, which means they can exist for a while, then they go away. I'll be talking more about the elements that we have on Earth. But, so they're numbered, 1, 2, 3, 4, 5, 6, 7, 8, 9. That number represents what? It represents the number of protons in the nucleus of the atom of that element. So hydrogen is element number 1. Each hydrogen atom has 1 nuclear proton. Helium is element number 2. Yeah, 2 nuclear protons. Lithium is 3, beryllium 4, boron 5, carbon 6, and so on. So these elements are very different from each other, right? Oxygen is element number 8. Each oxygen atom has 8 nuclear protons, and you need that to survive, right? 20% of our air is oxygen. When you breathe that in, you need that to survive. Fluorine is element number 9. It has 9 nuclear protons. Not much different from oxygen in terms of that. But if you breathed 20% fluorine gas, you would die pretty quickly. It's a highly toxic gas. So that one difference, that one proton in the nucleus, makes a big difference in how that atom interacts with other atoms. And instead of helping you survive like oxygen does, fluorine would kill you. So the number of nuclear protons in an atom determines how that atom interacts with other atoms. And we're going to see how that is, why it interacts. Different elements interact differently with other atoms when we get to the chemistry unit. That's one of the first units. Now I've got a pie chart here of the relative amounts of the various elements in our physiology, in our body. So you're entirely made up of atoms, right? So what elements are you made up of? Well, I like pie charts because they show relative quantities of different whatever. And here's the relative quantities. So this pie chart is the relative quantities of the various elements in your body. And you can see the biggest pie is most of the pie. Almost 2/3 of this pie is oxygen. Oxygen is by far the most abundant element in our bodies because most of our mass is water, and water is, by mass, mostly oxygen. So the bulk of your mass is oxygen, and then most of the rest is carbon, the second most abundant element. And we'll see why in the chemistry unit, why carbon's so abundant in our physiology and in all life. Hydrogen's the third, and then nitrogen, then calcium, phosphorus, and then on to the less abundant elements. So this box over to the right it's expanding those very thin pieces of pie on there, so it blows it up so you can see relative amounts of those lesser abundant elements. But this is just the 26 most abundant elements in our physiology. There's a lot more than that because most of the elements that exist on Earth are actually in our bodies. Like uranium you have trace amounts of uranium in your body simply because it's in the food that we eat, the air that we breathe in trace quantities. So it's in there, but a little over 24 or so elements have known functions in our physiology. And we're going to talk about some of those functions during the chemistry unit. But I just wanted to give you an idea of what you're composed of. There's a lot of elements in you, but it's really among the top 4 or 5 elements. That's the bulk of your mass, just those 4 or 5 elements. So how are these particles held together? Why do the electrons cling to the nuclei of the atoms? Why do the protons and neutrons that make up the nuclei, why do they stay clung together in the nucleus? Well, it turns out there's forces between these particles. And the force that holds atoms together and the force that holds atoms together into molecules and drives chemical reactions is called the electromagnetic force, or EM force. Protons are attracted to electrons through this EM force. And it's because these particles feel that force because they have a property called electric charge. You've probably heard of that before. Protons have a positive electric charge. Electrons have a negative electric charge. Positives and negatives attract each other. Positives actually repel other positives, so protons repel each other. Electrons repel each other. Neutrons don't feel this force because they don't have electric charge. So they just sit there in the nucleus, don't attract the electrons, but the electrons are attracted to the protons of a nucleus. That is why they cluster around the nuclei, and that is why atoms exist. So this table summarizes the nature of that EM force between different objects. So electrons repel other electrons, protons repel other protons, and protons and electrons attract each other. Electrons attract protons, protons attract electrons, and neutrons don't interact through that force with any of the particles because they don't have that property called electric charge. So here's a depiction of an atom. There's 3 protons in the nucleus. I'm not depicting the neutrons here, but there'll probably be 3 or 4 neutrons in the nucleus as well. And this would be a lithium atom because lithium is element number 3. So there's 3 electrons that surround the lithium nucleus, and I've got 3 blue minus signs to depict the electrons. The electrons are not at the positions of these minus signs. Actually, these 2 electrons fill this whole space, the spherical space surrounding the nucleus. This next electron fills a larger space. I'll talk more about why they do it that way when we get to discussion of electron shells and orbitals. But a lithium atom normally has, well, it always has 3 electrons. It always has 3 protons, and normally has 3 electrons because those 3 electrons are being attracted by the 3 protons. So here's 2 lithium atoms sitting near each other. So the electrons on the right atom are being attracted by the protons on the left atom, but they're being repelled by the electrons on the left atom, right? So they're not actually being attracted to that nucleus. And same with the other atom. The electrons there are being attracted to the protons of the right atom, but they're being repelled by the electrons of the right atom, so there's no net attractive force. So these atoms can exist near each other but not interact. They can also, though, if they're close to each other especially, they can interact with each other, and the electrons of one atom can be attracted to the protons of a neighboring atom, and they can form an atomic bond. So this EM force is responsible for making atoms. It's also responsible for holding molecules together. And I'll show you that we're made of a lot of molecules, and some pretty vastly complicated molecules. So, well, here's one of them. This is a hexokinase molecule. This is, you can see it's made of thousands of atoms that are held together by these atomic bonds. And these atomic bonds are electrons of one atom being attracted to the protons of a nearby atom, of a atom to which that atom is bonded. And so this is a very, very complicated molecule. This molecule is, I think it's an enzyme that is necessary for the digestion of glucose or something. I'm not a biologist, so I'm not sure what function it has in the human body. But there are thousands of different kinds of very complicated molecules in the human body that make us all operate. And this EM force is holding them together. It's also causing the chemical changes that are necessary for us to survive. So, for instance, this thing, when it processes glucose, glucose is one of the types of sugar that we use for energy in our body. And this processes it by changing the structure of that glucose molecule, by changing the arrangement of the atoms into different arrangements. That's all driven as well by the EM force. So the EM force is responsible for the existence of atoms, for the existence of molecules, of objects, which are many, many atoms, and for driving chemical processes. And you and I are chemical creatures, so we operate these very complicated processes that occur inside our bodies. It's all driven by this EM force. And so you may have never heard of it before, but it's a very important force in life and the way this all functions together. Okay, so the electrons are held to the nuclei by this EM force. What is it holds the nuclei together? The protons and neutrons are clumped together in this tiny, tiny nucleus at the center of each atom. Why do they stay together? I told you that protons actually repel each other by the EM force. So what holds them together? Well, it turns out, and this was discovered only in about 1960, that there's another fundamental force of nature called the strong nuclear force. And this table summarizes the way the particles interact with this force. So protons attract other protons, neutrons attract other neutrons, neutrons attract protons, protons attract neutrons. So it's an attractive force between these, what are called nucleons, protons and neutrons. This force is felt between particles that have another type of charge. It's not called electric charge, they call it the color charge, although it has nothing to do with color. It's just a name. But the electron doesn't have that type of charge, and so it doesn't experience that force. But this is what holds these particles together. Now, it's an extremely short-ranged force. It's only really felt inside nuclei between the particles that are within a nucleus. So if there are two atoms nearby each other, the protons over here and the neutrons don't attract these protons and neutrons over here. They have to be extremely close together. So that's just one of the characteristics of this force. So this is why nuclei are held together. So between the strong nuclear force and the electromagnetic force, the EM force, this is what holds everything together and makes things happen. The strong nuclear force, as we'll see later, is involved in nuclear processes, like the process that makes the sun shine, which is called thermonuclear fusion, and radioactive decay, and the nuclear processes that we use in our technology, like nuclear fission. Okay, I'd like to talk about one more force of nature, and that is gravity. Gravity is the one force that you've probably heard of before, and it's the one force you really are aware of. Your weight is the Earth's gravitational attractive force on your body. That's why when you jump off a chair, you go toward the floor, because you're being attracted through this fundamental force by the mass of the Earth. All objects that have mass attract all other objects that have mass. Now, it's actually an extremely weak force. These two objects both have mass, right? But I can't feel an attractive force between them. That's because it's a very, very weak force. And the only case in which we can feel that force is our own attractive force to the Earth. The Earth has a really large mass, right? Because it's a very, very large object. And so its attractive force on us is very noticeable. But the attractive force of ordinary objects on each other is not noticeable, yet it does exist, and during the gravity lecture I'll talk about that a little bit. So these are the basic particles and forces that make up everything in the world. And again, we'll see this stuff more as we go on through the units of this semester.